Yeah, so I'm going to talk about the mathematics behind the QR decomposition a little bit. In the QR decomposition, you're creating an upper triangular matrix R and Q, and so to do that, you see in the third line on this slide, it says update matrix A by A equals HA. So what that is saying is that you're updating the matrix A, your original matrix, by H, which is a householder matrix. It's a transformation matrix. And the householder transform you can think of it like a reflection matrix. And so there's this geometric representation of what a householder transformation does in 2 dimensions, but that can be generalized to many dimensions. And when you do that transformation, you can choose one based on the matrix A, so that when you multiply A by H, the result is that you zero out all of the elements below the diagonal. And so in the householder QR, you're iterating over every column of matrix A, and you compute in transformation matrix H, and then multiply the whole matrix by that. In the process, it zeroes out the rows below the diagonal, and then you go to the next column, and you keep doing that until you get to the upper triangular matrix R. Yeah, and then so the WY transformation comes into play in the block QR algorithm. So in the regular householder QR algorithm, you're iterating over columns, and you do the whole matrix update every column. In the block QR, you group the transformations by panels. So you split the matrix A into panels, and then you do the panel factorization, and then you create one, using the WY transformation, you create one matrix H or Q from the panel, and then you update the trailing matrix. And so that introduces a lot more parallelism, and the WI transformation is nice because you only communicate the householder vectors, which it's kind of like the factored form of the householder matrices during the communication step, which reduces your memory workload. Yeah. So in this slide, it shows the algorithms that we use, the key algorithms. Algorithm 3 is a block householder QR decomposition. So that's our highest level algorithm, and it incorporates the householder QR and WI transformation in line 7 and 8 of algorithm 3. And those two algorithms are algorithm 1 and algorithm 2. So algorithm 1 is the householder QR, and algorithm 2 is the WI transformation. And so combining these and then implementing it in C++ with CUDA, and using the parallelism to do matrix vector and matrix products, that's how we get our final implementation. Okay, so now I'm going to do a quick demo of running the code and showing you what the results look like. We're just going to do some small matrices, so it's pretty quick. Okay, so now to run it, you want to use release mode because debug mode will actually give you slower results. So select release mode, and then when you run it, you'll get this output here. So this is what our output looks like.